as we get closer and closer to the election, we're going to see more and more proportions in polls, and they're going to be have tighter and tighter margins of error. So the interpretation of these is going to get actually really relevant quite soon. Notice that the equality is again in the null hypothesis. Two of these are one-sided, and the last one is two-sided. And I haven't done much of that yet, but we'll do an example that goes through a two-sided test in some detail. Okay, so a couple of things to know. The standardized test statistic is yet again a z-score, and for proportions you only use z, never t. Does anybody remember the magic number for proportions? Where it means it was 30.
5.
But there's a wee bit of a difference from confidence intervals. With confidence intervals, you wanted 5 in each group, right? With a hypothesis test, you have to be able to set up your study before you gather any data. So you can't be sure that there's 5. Let's say you're trying to come up with some way to show that support for the Society for the Eradication of the Human Species is less than 1 in 10,000, which I suspect it probably is. What would then be the null hypothesis? I mean, what would be the alternative? You want to make the positive statement that support for the society is less than 1 in 10,000. And that statement has to go where?
Alternate.
Exactly. So the null hypothesis has to be that the proportion is greater than or equal to. Now, let's say you gather an immense sample and you find, 5 members of the society in your sample. Now imagine that instead you've got the same size sample but with no members of the society. Which one would be more convincing evidence that less than 1 in 10,000? Say you have a million people in your sample. In the first, you have 5 that are members. In the second, you have none. Which would be more convincing evidence that less than 1 in 10,000 support? The second, right? There are fewer, but that violates the whole confidence interval rule. The point here is, yes, you cannot create a confidence interval in the second case, but that's not really what you're interested in. What you're interested in is testing the statement that the proportion is greater than or equal to 1 in 10,000. And when you're able to reject that, you conclude that the proportion, in fact, is less than 1 in 10,000. So the positive statement you make is that fewer than 1 in 10,000 are members. Now, what does that tell you about the sample size? What is the minimum sample size needed? And for those of you who have not put your name signs up, I still appreciate it if you would. I have about 225 students, and I really don't have the capacity to break. I apologize for that. Okay, so yeah, 1 in 10,000 is our sort of magic cutoff, our PNOS. What then is our required sample size? 25,000? I'm sorry, 5,000?
Yeah.
5,000, okay. So if we had 5,000 observations, and there was exactly 1 in 10,000, then we have 1 in 10,000 times 5,000, and that's 0.5. So the expected number of individuals in our sample would be half, right? Half a person. Half a person's a bit short. The expected number of individuals in our sample that support the society has to actually be 5, not 0.5. So how large does our sample have to be?
100,000.
50,000. Exactly. So 1 in 10,000 times 50,000 is 5. And that is fine. So your minimum sample in this case, if you wanted to test this, would be 50,000. Which makes sense, because it's such a small proportion, right? You don't need such immense sample size if you're looking at the proportion of individuals who support either of the big political parties, for instance.
Now, would you have to keep sampling until you got 5, or just until you could have gotten 5?
No. Remember the first question, which would be more convincing? If you got none, or if you got 5 in a sample of 1,000,000? If you got none out of the 50,000, then that would be stronger evidence that he is less than 1 in 10,000 than if you got, say, 3, right? In fact, the only thing that matters is the expected. So the expected number of observations. As long as that's 5, you're good to go. But, so then if you get none, that's just gravy in this case. Okay with that? All right. Second thing to notice about this, and this is sort of both a philosophical and a math issue. With confidence intervals, the standard deviation, P bar, was P bar 1 minus P bar over N. Compare that to standard error when you're dealing with a hypothesis test, and tell me what's different.
It's about P-bar.
That's right. Here, we're using the sample to estimate the standard deviation of P bar, right? Over here, we're using the hypothesized proportion. Why? Why are we using the hypothesized proportion when we calculate the standardized test statistic?
We don't have a population yet.
We don't have a sample yet. That's good. We could wait until we actually got a sample and then estimate it, right? But, yeah, that's true. What else? There's a more fundamental reason even than that. What hypothesis are we operating under?
None.
The null, right? We assume the null is true and then we move forward. We assume the null is true, then we're also assuming that in fact the proportion in question is P naught. If in fact the proportion in question is P naught, then the standard deviation is driven by this. In fact, this is then the standard deviation in the population, which is reflected by the fact that we use sigma rather than S. And only when we've rejected the null hypothesis would you use the sample proportion to estimate any standard error. So that's the philosophical aspect. You can't use anything other than P naught until you have in fact rejected the null hypothesis that the proportion is P naught. Make sense? Once we've actually rejected, then if you want to create a confidence interval, you can do that, but that's then back into the methodology we've already covered. Other than that, everything else is virtually identical. We have two-sided rejection region, one-sided rejection regions depending on Z, or in fact two-sided. So looking at an example, let's apply this. We have a claim that 50% of accidents are caused by drunk driving, and so basically this up here is just black. You're confused by the numbers. Instead, these numbers are important. We have a sample of 120, of which 67 turned out to be caused by drunk driving. We're to test the claim using a significance level of 0.05. What is our default significance level? If you're not given anything? 5%. It's the same thing. Now, if in fact exactly 50% of the accidents are caused by drunk driving, how many of the 120 would be caused by drunk driving on average? 60. So the question is 67 far enough away from 60 for us to become suspicious of the National Safety Council's claim? And there's no right way for us really to tell that until we figure out how much that number varies, how much it moves around, right? If that number is always 60, then 67 is simply not believable. if that number varies, uniformly between 1 and 119, then 67 is obviously, it doesn't matter at all. But the question here is 67 enough of a surprise for us to conclude that the National Safety Council's claim that 50% of accidents are caused by drunk driving makes no sense? So, what is the appropriate null hypothesis in this case?
P0 is less than 67. Or P less than which one?
E.
Yeah, P. 67.
This is going to need a little bit of refinement, I'm afraid. Okay, so 67. First of all, P is a proportion. Yes? Proportions lie between which two numbers?
0 and 1. 0.67.
0.67. Okay, so 67 out of 100. How did you get 67 out of 100?
You 67 out of 120?
Okay, 67 out of 120. Is that what the National Safety Council is claiming? That less than equal to 67 out
Claim
of 120?
50%.
0.5. It's important to note what the claim is as distinct from what the sample is. Now, does the National Safety Council claim that less than or equal to, or more than?
Exactly.
Their claim is that 50%. So, I know it's kind of a painful exercise, but it's worth going through this in excruciating detail, because writing down the wrong hypothesis, it can really mess up your day. It's actually been a while, I think it was 96. I ended up spending half an hour working through an entire example, and then I realized I solved it backwards, hypothesis testing problem. So it's very easy to do, and I do it quite often myself. What is the alternative hypothesis then?
Not equal to 50%.
Not equal. Right. So that was step 1. What's step 2? Yes.
Could we, based on the conversation weeks ago about how, if we looked at the height of people coming in the room, if you look close enough, it's never the same.
Right.
Given the vast number of accidents, can't you say you're never going to have exactly 50% caused, and therefore, without any analysis, that ain't right?
Yes. You're quite right. But the question then is, can you tell them that they're wrong? If you can't tell them that they're wrong, then nobody cares. You just kind of have to live with letting them say what they want to say. So while I agree with you, philosophically, the probability that they're right is basically 0. The probability that they're wrong enough to matter might be quite low.
Gotcha.
But, well, I fully recognize that there are a bunch of these types of statements that sort of have to, all these principles have to fit together, and they do. It's just that there are a lot of them. So, that's our null and alternative. What is our step 2?
SDS.
That would be step 3. Rejection region, right. Now, does anybody remember why finding the rejection region should be our second step rather than the standardized test statistic? Because there's really, a lot of people do calculate the standardized test statistic first. I just argue that it's an additional aid in forcing yourself not to cheat to find the rejection region first. Why is that? Well, you have enough experience now with empirical rule and other standardized test statistics that if you calculate the standardized test statistic, are you absolutely sure that you won't be tempted to fiddle with alpha? Let's say you got a test statistic of 1.9. Wouldn't it be really tempting to use a cutoff of 1.645 rather than 1.96? If you really wanted to show that you could reject the null? Yeah, if you're not tempted, then you are superhuman, and I applaud you. But I can assure you that this happens all the time. And it's a pretty difficult thing to criticize because, you know, who's going to admit it? Okay, so under the null hypothesis, P bar has a distribution with a mean of 0.5. 0.5, good. And how do we get a rejection rate? How do we decide on an interval and test statistics such that we will reject the alpha? Alpha, good. And how shall we deploy alpha?
Alpha contains 5% of the curve.
Yep.
And D tells us that, or the chart tells us that that equates to 1.645.
In some senses, yes, but is this a one-sided or two-sided test?
Two-sided.
It's a two-sided test, so we need to deploy alpha to cut off both tails. And so instead of 1.645, our critical value is really only two that we use all the time. The other one.
1.96.
Exactly. And so the rejection region is what? Everything above and below. Broke my own rule there. That certainly wasn't 30 seconds. And now, what's step 3? Standardized test statistic. I believe we have that here. So we can calculate the standard error first, and I often forget to use p-naught. Try to make sure you put that on your curve sheet. Yeah.
I'm sorry, but I'm not, when rejection region equals, I'm not sure exactly.
Oh, minus infinity to minus 1.96.
Okay,
So everything below 1.96. Minus 1.96. Union 1.96 to positive infinity. So it includes everything from 1.96 to positive infinity.
thank you.
And then we calculate our standardized test statistic, which we know is z-distributed. 67 out of 120 minus the hypothesized 0.5 divided by our standard error calculated above. We get a standardized test statistic of 1.278. Is that in our rejection region? Is one, you might be shell shocked from the exam, I suppose, but is 1.278 inside this interval? Everybody see that in fact is not, right? 1.27.
No.
Why do I have so much trouble remembering the number? 1.278 is about here, right? Everybody happy with that?
No.
Clearly not in the rejection region, and therefore we fail to reject the null. The standardized test statistic is 1.278, not, this is step 4, not in the rejection region, which implies we fail to reject null. Questions on that?
Why did we not create, we don't have to create p-value.
There are two separate approaches to hypothesis testing that are equally valid. The traditional approach uses numbers along the real number line. The p-value approach uses areas. If you're going to, if you want to use the traditional approach, that's fine. You conclude, you're done. If you want to do p-values, you can use p-values without ever finding a rejection region. But, you know, one or the other you have to do. And we're gonna do both, because we can. No, well, because it's useful to have done both, so you can compare the two. Any questions? Okay, since that incredibly apropos question was posed, let us indicate 1.278. How can we, or what shall I shade in to indicate the p-value? Or what do we know about the p-value since we failed to reject the null? Even more basic.
It's not equal to 0.5.
The p-value is not equal to 0.5. Why is that? It's greater than alpha, that's right. Remember, the p-value is a probability, and 0.5 is it the proportion you're talking about? That's a number along the row number line, so that's a totally different thing. Now, how shall I shade the graph to indicate the p-value? What is more contradictory to the mean than the standardized test statistic of 1.278?
Everything to the right of 1.278 under the
Okay.
curve.
To the left of that,
And everything,
to the left of this house.
Minus 1.27.
you mean here? No. If you got a number that was further out here, that's more contradictory to the null than a number that's closer.
But then you would have rejected.
No, all I'm saying is that any number that is more contradictory to the null is in the interval below the p-value. So the p-value is the area above all of this, but even that is not the p-value. We're not done yet. Remember, we want all points that are as or more contradictory to the null than 1.278. And remember, 1.278 says we are 1.278 standard deviations above the mean.
You also need to do the same thing on the other side.
Exactly. So, we've got half the p-value here, and half the p-value here. Now, it's a common source of confusion, the interplay between alpha and the p-value. But notice that half of alpha is from here on out, right? Half of alpha. Half the p-value is from here on out, so there's a complete overlap. This half of the p-value completely dominates alpha, or half of alpha. But of course, if half of alpha is greater than half of, half the p-value is greater than half of alpha, then the p-value itself is greater than alpha. Just multiply both of those by 2. And in fact, that's what everybody does. You compare the p-value to alpha. And in fact, we can use this to find the p-value. How? What do we look up to find our p-value? Exactly. We look up the z-score, which is 1.278, the standardized test statistic. And if we do look up the standardized test statistic, what do we find? It's different depending on if you're in 9th or 10th edition, so whoever tells me first will deal with it. Use your favorite.
0.398.
Okay. In that case, you have the 9th edition. And in the 10th edition, you would see 0.898, right? Because it includes this piece as well, yes? Okay. Now, if half of the p-value is this part, and this area, between 0 and 1.278 is 0.398, how do we find half the p-value?
0.5 minus that.
0.5 minus 0.398, very good, which is 0.102, which means that the p-value is twice that, right? Yes? Any questions on that? Is that consistent with our previous conclusion to fail to reject the null?
Can you say that one time to get so half the p-value equals what?
Okay, so you have to start with the picture because otherwise none of this will make sense. The p-value is the probability under the validity of the null hypothesis, so this distribution, of getting a test statistic as a more contradictory than the one you got. You've got 1.278. More contradictory than 1.278 is considered to be greater than that number, right, further away from the hypothesized mean, or further away from the hypothesized mean on the negative side. Yes? Now, that means you have half the p-value on either side. By symmetry, these are identically sized, right? Look up 1.278, and that's what gives you the 0.398. But we know that this area, to the right of 0, half the distribution, this whole thing is 0.5. If this whole thing is 0.5, and we get rid of the 0.398, we're left with half the p-value. That's what this is saying. Half the p-value is then 0.5 minus 0.398, which is 0.102. But since that's only half, you have to multiply each side by 2, which gives you the 0.204. Okay?
Seeing fully how we got to this p-value, what does that mean to us?
Well, is it greater than or less than alpha?
It's less, no, it's greater than alpha.
Greater than alpha. Alpha is 5%, right?
Right.
So the p-value is greater than alpha, which means you fail to reject the null.
Okay.
And you can ask, well, what does this do for us after we've done all that? Nothing. But the whole point is not to do all this, right? The whole point is, in a computer, you can find the p-value immediately. You can pick alpha automatically and just conclude. It takes you less than 5 seconds. But a computer can't know which alpha to use. So a computer cannot do this automatically. You have to input alpha in order for it to do that. So, you know, in a computer-based world, this is easier because a computer can do all these calculations that we'd rather not do. I mean, calculating the p-value is painful. Interpreting it is usually pretty straightforward. For hypothesis tests in the traditional manner, the steps, each step seems to be okay, but the interpretation can seem a bit strange. So, what you prefer, it depends on you and tradition. Did that answer your question?
It did.
No, step 4 is here, just concluding. This is a separate approach. Using the p-value, you still have to state the non-alternative hypotheses. But then your second step is just to calculate the p-value. Well, you have to determine alpha, I guess. So you have to just pick alpha. And then find the p-value, and then find the reject, or fail to reject in this case. Yep.
How do we conclude that fail to reject non-hypothesis?
That's quite all right. Okay, so think in the traditional fashion. We need a standardized test statistic that is out here, right? Before we reject. Right? Alpha has given us this critical value. Yes? So we're not going to reject the null unless we get a standardized test statistic that is above 1.96 or less than minus 1.96. I'm not sure what that means. It's a yes? Okay. Okay. It's one of those interesting cultural mismatches. Okay, if that's true, then you see we're not going to reject the null here, yes?
Right.
Okay. Now, the p-value by definition is the probability under the validity of the null, in other words, under this distribution, of getting a test statistic more contradictory than what you just saw. So what's more contradictory than 1.278 standard deviations above the mean?
Oh.
1.279.
That's an example of something that's more contradictory. But what about 2 or 800?
Sure.
All those. So anything above this number is more contradictory. But in addition, anything below the corresponding distance below the mean is also considered more contradictory to the null. That's just by definition, but it's because of the shape of it's because of the null hypothesis, right? You're only interested in difference here. Yes?
Right.
Okay, now the question is, once you've defined it, you can just calculate the p-value. But once you've calculated the p-value, you can ask yourself, well, okay, let's move the test statistic here. Are we rejecting or failing to reject?
Failing to reject.
We still fail to reject, but is the p-value larger or smaller than it was?
P-value is smaller.
You see that? The p-value is getting smaller as our test statistic gets larger?
Right.
Because we only want the tails, right? Okay, it's smaller and smaller and smaller and smaller and smaller. At some point, we start to reject the null. In fact, we start to reject the null when our test statistic is right there. At that point, the p-value is alpha. Yes? Okay. When you get out here, when you start to reject the null hypothesis, the p-value is still the area to the right, or half the p-value is the area to the right of your test statistic. This is smaller than alpha. So it doesn't matter which you use, the numbers along the real number line or the p-value, because your conclusion is always the same. But really, the p-value is something you can interpret using this framework. So I would argue that this traditional approach is sort of the baseline, how people started. So I'm pretty sure that's true. And then you found, or people found that the p-value was just a useful tool to make things easier. Help?
Yes.
All right. Very good. Any other questions on?
So if the p-value is less than or equal to alpha, you reject?
Yes. You're gonna see different answers to that question with regard to equality. So usually you just say p-value is less than alpha, you reject. But it doesn't matter, because I've never seen equality. And of course, the probability of that happening with a continuous random variable is 0. In fact, when I first asked my econometrics professor that question, she just said, we'll calculate more decimals. Which to me seems like a somewhat wimpy answer. So, to give you a crisp answer, reject the null if the p-value is less than alpha. Fail to reject otherwise. But the fact is, equality is simply not an issue. It's sort of another one of those close enough to hypothesize mean. Other questions? Okay. Notice too that the structure of hypothesis testing for proportions is identical to the structure of hypothesis testing for means, right? Same 4 steps, same ideas behind p-values. In fact, pretty much the same distribution, or in fact, the same distribution for the standardized test statistic as for large sample hypothesis test for means. So the similarities far outweigh the differences, yes? And once you feel slightly more comfortable with this approach, you'll find that everything we do in regression is also the same structure, either a hypothesis test or a confidence interval. And once you learn how to think in those terms, then life gets much easier in terms of statistics. And I know you kind of have to take that on faith for the moment, but it does seem to be true. Okay, so this then is just the conclusion, and we just look at that. The last thing, the last theoretical part we want to look at is how to find the right sample size. And if you remember from confidence interval 2, we can specify the margin of error we want. And of course, the formula for the margin of error is z times s over the square root of n when we're dealing with means, and just solve for n. But the corresponding thing happens with proportions. So let's say that you decide that for the next poll, you want no more than some number of percentage points. Let's call that n. So this is your maximum margin of error. And so you want this to be true. But with a proportion, and a hypothesis test proportion in particular, you're going to then get z p naught 1 minus p naught over n less than or equal to n. Everybody agree with that? Okay. You can multiply across by the square root of n. then divide by m. And then, of course, we can square in order to find actual n. So n is greater than or equal to z over m squared p naught 1 minus p naught. And this is very useful, not only with regards to polling, but in any situation where you're just trying to plan, how large a sample size are you going to need? In addition, in proportions, you've got something else helping you plan. If you don't know anything about the proportion in the population, you can still use the P naught that gives you the largest possible sample size, right? Because that's conservative. And which P naught is that? Anybody remember?
50% of the sample size? And this would be 50% of the.
Just 50%, yes. 50%, the proportion 50% is the P naught that will give you the largest possible standard error and therefore the largest possible sample size required to minimize that margin of error. And that is our conceptual piece. So there's a lot that you do need to keep straight with regards to hypothesis testing. First of all, the null and alternative hypothesis. Is it clear what it is that determines what should be the null and what should be the alternative? My back is killing me.
Positive should go into alternative.
Exactly. The positive statement should go into the alternative hypothesis. So, I don't know if this helps you, it helped me. In a court of law, the positive statement you can make is that this individual is guilty. The negative statement is this defendant is not guilty, right? Any questions on that? Usually this is a huge source of confusion in the finding. The only thing that can mess up the notion that you're trying to show something, right? So for instance, if a marketing campaign, or somebody's trying to sell you on a marketing campaign, then you assume the marketing campaign doesn't work, so that they can claim that in fact the marketing campaign does work. Or, that's a good friend, or if, let's say you listen to pharmaceutical ads, which every once in a while I do because it's, well, kind of funny. And they make claims such as in conjunction with a healthy diet and adequate exercise, preparation something has been shown to be useful in lowering your cholesterol, which of course is true about, say, water. You'll also notice that, and this is even better, they'll often say things like, nothing has been proven to work better than blah to reduce heartburn, or I don't know, heart attacks, right? But again, nothing has been proven to work better. That's not really saying much of anything. Your null hypothesis then is that your product works at least as well, and you're basically testing that no other product works better. In that case, your incentive is to have the smallest possible sample size and make it as difficult as possible to even run the test. In which case, you're not going to pay to actually conduct a test in which where you're able to reject the null. So that type of claim is also pretty much worthless. Let me try to backtrack. You want to be conservative. You want to make sure that you think about the conclusions you want to draw when you set up your null and alternative hypotheses. But, especially since we're a business class, you have ongoing relationships with suppliers. Your null hypothesis may well be that the shipment is fine, right? Rather than start out with the assumption that the shipment that your supplier is trying to sell you a bill of goods. Yes? In addition, in quality control, the assumption has to be that the machine you're dealing with is producing products that are correctly specified. Let's say you're dealing with, and I have an example of this, so I'm sort of jumping ahead a little bit, but let's say that you're producing rulers that are precisely 1 meter long. there is apparently still a gold meter somewhere in Paris, even though I think we now define a meter as some distance for the
Atomic wavelength.
particle moves, yeah.
Yeah.
But if you produce rulers, is it clear to everyone that you're not gonna get the exact same length each time? Right, I mean, ideally you get that, but even when you're producing something that's supposed to measure length, you're not gonna get the same length each time. But what can be a little disconcerting is that your machine could be uncalibrated. For instance, let's say that the machine just whittles down what a meter means, but it's so little that you can't notice day after day, until of course you're 30 years older and a meter is this big. That's, it could happen. But in order to make sure it doesn't, one thing you can do is you can measure. You can take a sample every day or every week or something and calculate the sample average length. Yes? When you do, what is the null hypothesis?
Equal to the length, the meter.
The length is equal to 1 meter. Yes. Doesn't that seem like you're setting yourself up to succeed? Doesn't that seem non-conservative and at odds with what we just talked about? A little bit? So the question then is why? Why would we do such a thing?
Low cost of getting.
No, it's even more basic than that. The problem is this: if that wasn't your null hypothesis, what would be?
That's not,
That you're making bad product.
No, Mary?
that's not equal to a meter?
Exactly. That mu is not equal to a meter. But not equal to a meter is every single other value other than precisely 1 meter, right? Arbitrarily close. You'd never be able to reject, ever. So you would not be able to conduct a hypothesis test at all if you had any other null hypothesis. Actually, it took me a while to figure that out because nowhere in read statistics does anybody bother to tell you that in fact you do have to have a distribution of the test statistic. But that is the primary requirement. You must have a distribution or a test statistic under the null hypothesis. And then and only then, you need to think about which conclusions you want to draw. Right? You want to be typically want to be conservative, but not always, not with suppliers. But typically, you want to, if somebody's trying to make a claim, a positive claim, that you're asked to believe, then you should put that in the alternative and make sure that they can prove it. Yes? Or at least find support for it, for their claim. Now, if you have one-sided tests, you can flip these around, and that's where it gets tricky. If it's two-sided, it's actually easier. So, null and alternative, those are really crucial. The 4 steps of hypothesis testing, also crucial. Stating your null and alternative, finding the rejection region, calculating the standardized test statistic, concluding. The most difficult part about those 4 typically seems to be diagnosing. So, let's say you have a proportion problem on the final exam, but this could be in real life too, and you realize that, wait, I don't know what S is, or for whatever reason, you don't have S. It's actually more likely than the final. What's the problem?
We don't have an S. Standard deviation.
Right, I give you all sorts of information about P naught, P, but I don't say anything about the standard deviation.
You don't need.
Exactly. You don't need it. There is no S when you're dealing with proportions. The standard error is a function of the proportion. Yes? So you're good to go on that. But it's a really common question to be asked on the final, or for me to be asked on the final. So make sure you put that on your crib sheet.
Will you go through that one again? It
Sure.
lost me.
That hypothesis test right there, right? You're never given an S. If there is no standard deviation, no sample standard deviation, no parent population sigma in this case, yes?
True.
And you don't need it. It really is not something, it's simply not a factor in this particular methodology. The standard error is a function of the proportion. Remember, the parent population is, you can think of it as very digital. It's either 0 or 1. Every single member is either 0 or 1. So there's no standard deviation within that. You do need to know what a p-value is. You need to know, you need to be able to find it, you need to be able to compare to alpha, and you need to be able to conclude correctly. A common tool, a mnemonic to help you keep things straight, is to say that the p-value is a probability that the null hypothesis is true. Is it? In reality, what is the probability the null hypothesis is true?
1 or 0.
1 or 0, right? It's a statement about nature. It's like saying there is intelligent life around Alpha Centauri or wherever. There either is or there's not, but we don't know. Yes? P-values. There's something. Okay. Let's say you've rejected the null hypothesis. Is it now possible to make a type 2 error? No. A type 2 error is failing to reject a false null. So it's a good idea to recall that, and frankly I find it kind of comforting, that once you've concluded, there's really only one kind of error you can have made, right? If you reject the null hypothesis, then you may have rejected incorrectly, right? In which case you've made a type 1 error. If you fail to reject, well, you may have failed to reject when you should have rejected, in which case you made a type 2 error. So it is important to keep those things clear and know the relationship between those two, and in particular how that drives alpha. Again, what is the relationship of alpha to the types of errors?
Rejecting the null.
Not just rejecting, but rejecting the null when the null is true. So type 1 error. It's the probability, actually the maximum probability of a type 1 error that you're willing to live with. You can always drive it smaller. Like for instance, if you go to a doctor, you have a null hypothesis that you're sick. If you decide, I want 2 doctors to tell me, so get a second opinion. What you're doing is you're driving alpha down. You're making it less likely that you make a type 1 error. In other words, you make it less likely that you're told that you're healthy when in fact you're not. That's usually the more dire type of error in medicine. What else? Diagnosis. I trust that most people are comfortable seeing whether or not we're dealing with a hypothesis test or a confidence interval. In a hypothesis test, you're for one thing told to mu0 or p0, right? So there are certain hints that you have to have. But where things get tricky is, especially when you're dealing with means. And this is true for both hypothesis tests and confidence intervals. When you have means, you have the whole question of sample size. If you have a small sample, then you need to ask yourself what? What's the next question?
Is it uniformly distributed?
Distribution of
Population.
the population. And if you don't have a normally distributed population, then what?
More data.
Increase the sample size or go home or stop, right? If you do have a normally distributed parent population, there's yet one more question you need to ask yourself.
Do you know the standard deviation?
What's that?
Do you know the standard deviation?
Yes. Do you know the standard deviation of the parent population? If you do, then you're again back to using a z-score. I mean, a normally distributed random variable, you're good to go. If you don't, you have to estimate sigma using S, and that standardized test statistic is distributed how? What distribution do you use?
T,
T. Very good. With how many degrees of freedom?
n minus 1?
Very good. So you have it all, it's just a question of dredging it up at the right time. And if I haven't made this clear, for the final, you'll be given, or you'll be allowed to bring 4 sheets of paper, 8.5 by 11, both sides, in your own handwriting. Has to be your handwriting. Because I've had people bring in pages this big and then basically created entire texts. They've miniaturized and then brought huge loops to try to read the book. You don't have time to do that on final, so there's no point. But on the other hand, I've never ever had somebody fill up 4 pages and tell me they needed a 5th either. So, and obviously you're not asked to put the tables or anything on the crib sheets, you'll be given those. So put the diagnosis on the crib sheet and put, all the symbols and formulas you need. And then just remember how to think. That's the important part.
Speaking of the final, a little early to be talking about that, but
Never too early.
as we're recovering from the most recent test, and I think recovering is a safe
That's the
word.
second one.
How in depth should we expect it to be? Because that took some work. This recent test couldn't have been done in 3 hours. I couldn't have done it in 3 hours.
What's the possibility that any one of us could
Actually, you probably could. But you would have studied very differently. You study differently for an in-class than an out-of-class test. But the other thing, remember, this is a cumulative final. So there won't be any one question as long as the expected value of imperfect information or perfect information.
Won't be?
No, because then I'd have to have, I might be able to get something interesting if I budgeted an hour to ask that type of question, but we've already asked that, so I'm not as likely to ask that again. I might ask some subset, one question, or start you off by saying, okay, the expected value of a project is this much. If you know the following things, you get the expected value here. What's the expected value of imperfect information? And, question like that, you just have to pick out the pieces and tell me, subtract one from the other, something like that. Might not be quite that simple either, but my point is, they're not going to. I've been doing this for a while. Typically, the first person leaves at about 90 minutes. And not in disgust, although I'm always asked that. If the ones who leave in disgust tend to stick around only about 15 minutes. Okay. Usually, the first person does in fact leave at between 90 and 2 hours, 90 minutes and 2 hours. And then usually most people are gone by 2.5 hours. There's always, a good half dozen that like to check their work until the clock runs out, which frankly means like to second guess yourself until the clock runs out, which can be a little painful, but it's rare that it's a time issue. Don't get me wrong, it won't be, you'll still be under time pressure,
Right.
but people do answer something.
Is it,
The 2%.
are you going to grade subjectively on what kind of questions you get right? For example, if you are able to answer regression questions?
Answer grade subjectively, as in, ooh, I don't like the way you wrote that I.
No, I meant that which concepts you are clear or not, kind of thing. Which chapters.
Well, I think that has more to do with how I make the test. The way I make the test is entirely subjective, right? I will pick out what I think is important in the type of question, but when I grade, I do try to follow. My rule is to try my very, very best to grade everyone equally harshly. The level of harshness is not as important as me doing it the same way everywhere. So, of course, then at the end, I always scale it, so it doesn't really matter. Yeah, was that what you were getting at? Okay. All right, yes?
You said that test grades won't be until after the weekend?
But what I said was, while normally I would schedule a huge chunk of the weekend to grade, I have the vast majority of the weekend already scheduled. And so, unfortunately, it's probably going to take a little bit longer to get these grades out, unfortunately. Other questions? Okay, let's take another break, and then we'll do problems.